So, welcome to lecture series on advanced linear algebra. In our last lecture, we have proved one results. If T be a linear operator on a finite dimensional vector space V over the field capital F, such that the minimal polynomial of the T is a product of linear factors, that is, if P is the minimal polynomial, P is equal to x minus C1 power R1 into x minus C2 power R2 and x minus Ck power Rk, where C1, C2, Ck are distinct eigenvalues, or you can say distinct constant from the field capital F. And if W be a proper subspace of V which is invariant under T, then there exists a vector alpha belongs to V, certainly non-zero vector alpha, because I have taken W is a proper subspace. So, there is a non-zero vector alpha in V such that the T conductor of alpha is a linear polynomial of the form of x minus C. I mean to say alpha does not belongs to W, but T minus Ci when it is operating on alpha will be in W, where C is basically some eigenvalue of the operator T. We shall utilize this result to prove the existence of simplified form of a linear operator defined over a finite dimensional vector space. I will talk about the triangulability of the operator T, please. So, this is a nice results I can write in terms of theorems like this. Let T be a linear operator on a finite dimensional vector space capital V over the field capital F. Then T is triangulable if and only if the minimal polynomial say P is product of linear factors, that is P equal to something like x minus C1 power R1 into x minus C2 power R2 and x minus Ck power Rk. Certainly C1, C2, Ck will be eigenvalue or characteristic value of the operator, and Ri I equal to 1 to k is the positive integers, okay, and C1, C2, Ck are distinct eigenvalues, please. If it is a characteristic polynomial, then I could say R1, R2, Rk are the algebraic multiplicity of the eigenvalues C1, C2, Ck, please. So, where C1, C2, Ck are distinct constants from the field capital F. How to prove this result, please? To prove these results, we shall use our previous results, that if T be a linear operator on a finite dimensional vector space and the minimal polynomial is product of linear factors, and if you consider W is a proper subspace of V, then there exists an element alpha belongs to V such that T minus C I operating on alpha will be in W. So, I shall use these results or this lemma repeatedly to get the corresponding order basis under which the operator will be triangulable, please. So, let me consider if part. Given the minimal polynomial of T, that is product of linear factors. Okay, it is given to us, that is P equal to x minus C1 power R1 into x minus C2 power R2 x minus Ck power Rk. This is given to us. We have to construct an order basis. This is B consisting of alpha 1, alpha 2, alpha n if dimension of V is n such that matrix representation of T with respect to order basis B will be of the form of something A11, A12, A13, A1n, then 0, A22, A23, A2n, and like this ANN, and this is 0. So, I will have a triangular matrix like this. We have to construct an order basis B consisting of alpha 1, alpha 2, alpha n, provided the dimension of the space is n, such that the matrix representation will be triangular matrix. This implies we want to show the T of alpha j, T of alpha j will be A j 1 alpha 1 plus A j 2 alpha 2 plus A j j alpha j. Okay. So, we want to show that there exists an order basis alpha 1, alpha 2, alpha n such that matrix representation of T with respect to that order basis is like this. So, certainly this A1, A22, ANN will be the characteristic values of the operator. Okay. So, this will construct by repeated application of the previous results. This will be done by repeated application of above lemma. So, let W is equal to 0 subspace, 0 subspace please. So, one can find a vector say alpha 1 belongs to V and alpha 1 not equal to 0. Using above lemma, we have t minus some eigenvalue. So, let me consider say c, t minus c I operating on alpha 1 will be equal to 0, because it will be in W. So, means t minus c I operating on alpha 1 will be 0 please. So, let c is equal to a 1 1. This implies t alpha 1 is equal to c alpha 1. Let c is equal to a 1 1, just renaming the constant please. Now, consider W 1 as linear span of alpha 1. W 1 is basically another subspace of vector space V, which is like this, W 1 equal to linear span of this one please. Now, question is whether W 1 is invariant under T, whether W 1 is invariant under T. See, the way W 1 has been constructed, it is basically eigenspace associated to eigenvalue C equal to A 1 1. Since W 1 is eigenspace associated to eigenvalue A 1 1, so W 1 is invariant under T. Now, W 1, if the dimension of the vector space n equal to 1, then we are through it here. Now, W 1 will be proper subspace of V. If dimension of V which is equal to n is strictly greater than 1. So, this implies there exists a vector 0 not equal to alpha 2 belongs to V such that alpha 2 does not belongs to W 1 please. So, according to above lemma, there exists an eigenvalue say A22 such that T minus A22 I operating on alpha 2 will belongs to W 1. So, this implies T minus A22 I operating on alpha 2 will be equal to something like I can say some scalar multiple to alpha 1 please. So, I can say A21 alpha 1, where A21 belongs to the field capital this one. So, this implies T alpha 2 equal to your A21 alpha 1 plus A22 alpha 2. Repeat the procedure. So, but before the repeating procedures, I have to say that let W 2 is equal to linear span of alpha 1 and alpha 2. Claim W 2 is invariant under T. How it is invariant under T? For any beta belongs to W 2, that is beta will be of the form of something C 1, okay, something D 1 into alpha 1 plus D 2 into alpha 2 type, because linear combination of alpha 1 alpha 2 and D I belongs to the field F. So, T of beta will be equal to T of D 1 alpha 1 plus D 2 alpha 2, which is equal to D 1 T of alpha 1 plus D 2 T of alpha 2. So, this implies that it will be D 1 T of alpha 1, which is equal to A 1 1 alpha 1 plus D 2 into T alpha 2 is equal to, I can say here, A 2 1 alpha 1 plus A 2 2 alpha 2. So, this is equal to, again I am getting D 1 A 1 1 plus D 2 A 2 1 into alpha 1 plus D 2 A 2 2 alpha 2. So, this implies T beta belongs to W 2. So, W 2 is T invariant. Okay. So, now I can repeat the same procedure. So, if W 2 is a proper subspace of V, then we can repeat the above procedures to get a vector alpha 3 belongs to V, but alpha 3 does not belongs to your W 2. However, there exists eigenvalue say A 3 3 belongs to capital F such that T minus A 3 3 I operating on alpha 3 will be in W 2. Continue the procedure. After nth step, one will get n vectors alpha 1, alpha 2, alpha n such that B equal to this is linearly independent. Linearly independent. How it is linearly independent? Already I have given the proof, the way we have constructed the vector alpha 1, alpha 2, alpha 3. I have utilized the concept that alpha 1, alpha 2, alpha n are linearly independent. So, we will get n linearly independent vectors alpha 1 to alpha n, which are linearly independent, and T of alpha j equal to sigma a I j alpha I equal to 1 to j. So, this implies coordinate matrix of T alpha j with respect to order basis B equal to your A 1 j, A 2 j and up to A j j 0 0 0 please. So, I will have a column matrix like this please. So, this implies matrix representation of T with respect to order basis B will be of the form of A 1 1, A 1 2 and A 1 n 0, A 2 2, A 2 n 0 0, A 3 3, 3 n, A n n, this is 0 please. So, I will have the matrix structure is equal to like this. Now, it is other way, only if given that there exists an order basis B consisting of say alpha 1, alpha 2, alpha n for vector space V such that the matrix representation of T with respect to the order basis equal to triangular matrix, that is A 1 1, A 1 2, A 1 n 0, A 2 2, A 2 n and A n n 0, this one. We have to show that the minimal polynomial is product of linear factors. Certainly, characteristic polynomial of triangular matrix so this is equal to say capital A is a f is equal to x minus a 1 1 into x minus a 2 2 and x minus a n n. It may be possible that these characteristic values are repeated. So, if it is repeated, so it may be possible that T has k distinct eigenvalues C1, C2 and Ck with algebraic multiplicity say E1, E2 and Ek. So, then f will be equal to x minus a 1 1 into x minus a 2 2 into x minus a n n is basically same as x minus c 1 power say E 1 into x minus c 2 power E 2 and x minus c k power e k. So, the characteristic polynomial will like this thing please, and this c 1, c 2, c k are coming from aii, I equal to 1 to n please. Let p be the minimal polynomial of t. Then we know p divides f, though this implies p has to be of the form of x minus c 1 power some positive integer r 1 into x minus c 2 power r 2 into x minus c k power r k. Here sigma e I equal to 1 to k equal to n, but here sigma r I equal to 1 to k is less than or equal to n please. So, we see that if T is a linear operator defined over a finite dimensional vector space over the field f, and if its minimal polynomial is product of linear factors, I mean to say the minimal polynomial is factorizable over the corresponding field, then the linear operator is triangulable. That is, there exists an order basis under which T can be represented by a triangular matrix. So, for examples, let A equal to this be the matrix representation of a linear operator T on say R 3, okay, over the space of 3 tuple space please, over the field real number. One can easily calculate determinant of x I minus a, which is equal to minus 1 to the power 3 into determinant of, and this is minus x 1 0 to minus 2 minus x 2 to minus 3 to minus x. So, this is equal to, we will have simply x skew, we will have this is equal to x skew, maybe plus or minus on this thing. So, this implies characteristic polynomial of A is x skew. So, characteristic values are 0 0 0. Now, we want to find out an order basis consisting of alpha 1, alpha 2, alpha 3 such that the matrix representation of T is a triangular matrix. We want to find out an order basis, say capital B, consisting of alpha 1, alpha 2, alpha 3 such that matrix representation of T with respect to that order basis will be a triangular matrix, a triangular matrix. So, I can write like this thing please. That is certainly diagonal entry will be 0 0 0 please. Okay, how to find it? So, first I have to find out the eigenvector associated to eigenvalue equal to 0, that will give me the alpha 1. So, eigenvector associated to 0 eigenvalue please. So, this means that I will have 0 1 0 2 minus 2 plus 2 2 minus 3 plus 2 I think, yeah. So, this is a minus alpha I. So, it is this into vector say x 1 x 2 x 3. So, this will be equal to 0 a minus c I x equal to 0. So, that is why, because c equal to 0 I am getting like this thing please. So, this implies I will have the system x 2 equal to 0 and I will have x 1 plus x 3 equal to x 2. Third one will give me 2 times of x 1 plus x 3 equal to 3 times of x 2, but x 2 equal to 0. So, this implies that x 1 is equal to minus x 3. So, alpha 1 I can construct is like this, x 1 equal to 1. So, 1, x 2 equal to 0, x 3 equal to minus 1, this type of transfer please. Okay, so, I am working for the matrix A. So, this is basically the associated to the matrix A only, alpha 1 equal to 1 0 minus 1 transpose please. Now, second one I have to obtain, let W 1 is equal to linear span of alpha 1, that is a scalar multiple of 1 0 minus 1 transpose please. So, if it is, then I will have many solutions no doubt, but I can take scalar quantity c equal to constant equal to 1, I can have like this, again system x 2 equal to, okay, I will have basically a capital X equal to alpha 1 say. So, this means that I will have x 2 is equal to alpha 1 is 1. So, x 2 is equal to 1, then I will have other equation 2 times of x 1 plus x 3 minus 2 times of x 2 will be equal to 0, and third equation is 2 times of x 1 plus x 3 minus 3 x 2 equal to minus 1. So, this implies that I will have x 2 equal to 1 and this is giving me x 1 plus x 3 equal to x 1 plus x 3 is equal to x 2, which is equal to 1. So, if I put x 3 equal to 0, x 3 equal to 0, then I will have x 1 equal to 1, because the third equation also will give me same, because 2 x 1 x 2 is equal to 1. So, it will be minus 3. So, 2 into x 1 plus x 3 equal to 2. So, I will have x 3 equal to 0 and x 1 equal to 1. So, this means alpha 2 I can construct as 1, x 2 is equal to 1, 1 and 0, alpha 2 is equal to this one. So, the construction that alpha 2 such that here I have, see, a minus 0 into I alpha 2 must be equal to scalar multiple of alpha 1. So, it is equal to I can here 1 here. So, that is what I have taken alpha 2 is equal to, you can see it is satisfying this relation please. So, alpha 2 equal to this quantity. Now, alpha 2 is known, alpha 3 is also known. Now, let me consider again Ax equal to linear combination of alpha 1 plus alpha 2. So, let me put alpha 1 plus alpha 2 only. I have taken the constant value 1 only. So, if I took like this, if I take like this, then this means that I will have this is equal to alpha 1 plus alpha 2. So, alpha 1 is 1 0, okay, 1 0 minus 1 transpose plus 1 1 0 transpose. So, this means that I will have the column that is 2 1 minus 1, 2 1 minus 1 transpose please. So, Ax equal to 2 1 minus 1. Now, I have to solve this system please. If I solve these systems, I will have what? X2 equal to 2 times of x1 plus x3 minus 2x2 equal to 1 and 2 times of x1 plus x3 minus 3x2 equal to minus 1. Now, I have to solve this system please. So, if I substitute x2 equal to 2, this implies that x1 plus x3 equal to, so it will 5, right. So, 2 times of x1 plus x3 is equal to 5, second equation says. Third one also give me, so put x2 equal to 2 minus 6 plus 5 please. So, again same equation. So, what I will do? I will take x1 equal to 0, putting x1 equal to 0, I have x3 is equal to 5 by 2. So, I will have alpha 3 is equal to x1 0, x2 2, x3 is equal to 5 by 2. You can check A into alpha 3 is equal to column 2 1 minus 1 please, linear combination of alpha 1 and alpha 2 please. Now, B is equal to this alpha 1, alpha 2, alpha 3 such that the matrix representation of T will be a triangular matrix, will be a triangular matrix please. So, what is the triangular matrix? So, diagonal entry will be 0 and because eigenvalue is 0 and your this one will be what? We have to see what is the coefficient of your T of alpha 1 and T of alpha 2 and T of alpha 3, so that it will give me a triangular matrix please. So, you have seen that one can find an order basis under which the operator can be represented by a triangular matrix, but this representations is not unique because it depends on the constants, scalar quantity please. You take different scalar, I have taken 1 and coefficient 1 and 1, if you take different coefficient I will have different solution please, but it is possible to have a order basis under which one can have the triangular representation of the operator please. So, we will continue the applications of invariant subspace in our next class also please. Thank you.